Hello everyone, welcome to the IAL Physics Unit 2 predictions for May 26. That is your exam tomorrow. So, um, in this video, I will not be getting into the depth of any question because this is not a revision video. This is just what my prediction is for your exam. All right, but I can guarantee you a lot of questions that I'll be discussing and a lot of concepts that I'll be touching today will be definitely coming in your exam tomorrow. That you can rest assured. Now, what I have done for you is I have made a full paper solution video of the most recent paper. The most recent will be tomorrow's one, but before that was Jan 26. This was an incredibly important paper. So please go through the whole video solution so you get an understanding of how I solve a specific paper. And I think this will be immensely useful for you. Then what I have also done is I have compiled all the frequently asked questions and answers and interpretations of Unit 2, all the topics of Unit 2, electricity, waves, and nature of light. And you'll get everything in this package. And the download link is given in the description. I can guarantee you, you'll get a lot of questions common in your actual exam. If you pair this video with the two other revision videos that are on my channel. One is last minute revision video and the other one is the full syllabus revision video, both of which will be immensely useful to utilize all of the resources that I have, uh, given to you and you have at your disposal. And I can guarantee you it will be a better exam, okay? Better than what you were expecting. All right, so there are three topics of Unit 2. Those are electricity, waves, and nature of light. And what I am guessing will be the format of the paper is there will be a burst of short questions in section B. Mostly we'll be discussing topics of section B because that's what's most important. Burst of short answers, short questions and answers, and the length and the difficulty will progressively increase with each question. Okay, this is my prediction. And I read all of the comments that you post in my videos, and I have a small request for all of you. Do mention where you're watching my videos from. I really love to see where people are watching my videos from. All right, now. So the first topic of electricity that I want to cover is the transport equation. And the transport equation is I equals to NAVE. And you need to know the definitions of each of these terms. N is the charge carrier density. There is another name in the most recent papers. N, what I'm noticing is they're calling N number of conduction electrons per unit volume. A is the cross-sectional area. This is what you mean by A. V is the drift velocity, and E is the charge of an electron. And I can guarantee you there will be some definitions in your actual exam. Make sure you have the definition sheet memorized inside out. And the questions, there can be some very straightforward mathematical question, or what they can do is they can elevate a concept. For example, let's say you have two pieces of wires, okay, connected in series, and the same current, of course, since they're connected in series, the same current flows through both wires. The question may ask, what will be the drift velocity in the second wire? And of course, it has to be mentioned that both wires are made from the same material. So recall the equation, I equals NAVE. Since the current remains the same for both, since this one has a higher or larger cross-sectional area, the drift velocity through this one would be smaller. So like I said, with this transport equation, you can have straightforward calculation questions or a little bit advanced theoretical questions like this as well. Let's move on. Now, every time you come across the term resistivity in a question, there is literally no other equation other than this one, resistance equals rho L by A. And a lot of times, the question does not give you the area. What they give you is the diameter. And since you have already set for your Unit 1 exam, you should know what is the equation that links diameter with area. It's pi d square by 4, right? So one more time, every time you come across the term resistivity, there is literally only one equation you have to recall. That is resistance equals rho L by A. One other thing I forgot to mention is you'll get a free formula sheet because Unit 2 is heavily dependent on equations. You need to have all of the equations memorized. You'll get the definition sheet, then the formula sheet, complementary with the fact sheet, FAQ sheet. Let's move on. Okay, so take a look at these two circuits, right? This is the concept of potential divider calculation. Which equation do you recall in which situation? Let's say for the left one, if I want to find out V1, you go with V1 corresponds to the resistance R1, and R1, what percentage or proportion does R1 carry out of the total resistance? And since they're connected in series, the total resistance would be R1 plus R2. So we all know that in a series circuit, the PD gets shared according to the ratio of resistance. And this is what you mean by ratio of resistance. So in this ratio, the total PD, VT, is shared. The same thing goes for V2. This is VT. And the same thing applies for V2. V2 corresponds to R2 divided by, so R2 carries what percentage or what proportion of the total resistance? Total resistance is R1 plus R2. And in this proportion, the total PD or the total voltage will be shared or will be allocated towards V2. Now, this one is a bit different. This is very common. This is like really common. This is not so much. What about this one though? Here, the only difference you can spot is the total PD is not given, the EMF is not given. And when the EMF is not given, and when you have a circuit like this, the equation that you recall instinctively is V1 by V2 equals R1 by R2. So you use this equation when the total PD is not given. Let's move on. Now, it's the same concept, the potential divider concept, but this time with a semiconductor. This is also a very commonly asked question. So for this concept, let's say this is a thermistor, okay? So the question might ask you, what happens to the voltmeter reading if, let's say, the temperature of the thermistor increases? So I'll show you a sequence of events, right? So if the temperature increases, you know from your IGCSEs that as the temperature increases, the resistance of the thermistor decreases. And guess what? This is a series circuit. And in a series circuit, the higher the resistance, the greater the PD across it. And the converse also holds true. If the resistance of the thermistor decreases, the PD across the thermistor must also decrease. But the total PD must remain constant. To keep the total PD constant, if the PD across thermistor decreases, the PD across the resistor should increase, so the voltmeter reading should increase. And I showed you with a thermistor, the question can be a variant. There can be a variant of this question, and they can ask you about an LDR. And instead of temperature, they can ask you about light intensity. The core principle and the concept remains exactly the same. Now, let's talk about filament bulbs. So when it comes to filament bulbs, always remember a large increase in voltage causes only a small increase in current. And of course, it's a non-ohmic conductor, right? So you see from the VI relationship, a large increase in voltage only causes a small increase in current. Why though? Because the resistance does not remain constant. The resistance increases. And this used to be a very common graph. So it's been years that there has been no question associated with this. So what happens is this is a current time graph for a filament bulb. When there used to be a very common question back in the day that when is a filament bulb most likely to break? When it is switched on or later? So the answer is always when it is switched on, because when it is switched on, you see there is a spike. Current drastically increases. And according to P equals I square R, as current increases, the power dissipation also increases. So it heats up the most when it is first switched on. Next, you need to know about this device. This is also used to be a very common concept. So this is just my contingency plan that this might show up in your exam, right? I wouldn't say most likely, but definitely this is in the syllabus, so we have to cover this. So rheostat can be used in two different ways. One is as a variable resistor, the other is as a potential divider. And what is the difference? Let me just show you from here. Okay, so this is where you use a rheostat as a potential divider, and this is where you use a rheostat as a variable resistor. This is more common. This is also very important. For example, just look at the two graphs that you get using a variable resistor and a potential divider. Using a variable resistor, you only get a small range of values. You don't get any values near zero or near the maximum PD. Whereas when you use a potential divider, you get a wider range of values. For example, if I want to learn about the relationship or study or investigate the relationship between current and voltage for a diode, right? So I need to start from zero. If I use a variable resistor, it's going to be very difficult for me to get values near 0 volt, right? So I will definitely use a potential divider instead, which gives you a wider range of values. Let's move on. Okay. This, I feel, is most likely to appear in the exam in some capacity. Okay, so this is a very basic internal resistance concept. Okay, they can ask you draw a diagram that you'll use to investigate internal resistance, and this is the diagram that you draw: a battery and a voltmeter in parallel, a variable resistor, and an ammeter in series. And if you vary the resistance of the variable resistor and if you record values of current and voltage, this is the graph that you get. And let me give you a rundown of the shape of the graph, right? So this battery has an EMF. This EMF is actually shared between two components. One is inside the battery, as in the internal resistance. So one part of the EMF goes towards the internal resistance. The other part goes towards the load resistor. Let's call that V capital R. Okay, and since these two are connected in series, the same current flows through both, right? So EMF equals, instead of V, I can break this down as IR. R stands for the internal resistance plus VR, and this is the load resistance, right? So if I make V the subject of the equation, V is equal to, bring this to the other side, minus IR, and if I flip the positions, minus RI plus EMF, and guess what? This is in the form Y equals mx plus C. So if I place V on the y-axis and I on the x-axis. The gradient, actually the negative of the gradient gives the internal resistance, and the y-intercept gives the EMF. So just by looking at this graph, it should be very obvious to you that 1.5 is my EMF, and if you find out the gradient, that will give you the internal resistance. So this is very common. What's not so common is this, everyone. The power dissipation. How does it vary with load resistance? Initially it increases, reaches a peak, and then decreases. So always remember, this used to be a common concept, but it's been years. This question has not appeared in the examinations. So I just thought of introducing this, reintroducing this. So always remember, the power dissipation in any circuit is maximum when the load resistance is equal to the internal resistance. And what can also appear is some advanced theoretical concepts of internal resistance. Instead of a variable resistor as the load resistor, you can have an LDR and you can have a thermistor as well. So the trigger for LDR and the trigger for thermistor will definitely be different. For the LDR, the trigger is light intensity. So if intensity, let's say, increases, the resistance of the LDR decreases. If the resistance of the LDR decreases, the total resistance of the circuit also decreases, which increases the current. If the current increases, the same current flows through this internal resistance. So V across internal resistance, which we call the lost volt. If the PD across this increases, guess what? The PD across the thermistor, sorry, PD across the LDR will decrease. And what do you call this voltage? This is called the terminal PD, right? The terminal PD decreases. Don't mix it up with terminal velocity. This is the terminal PD. And they can give a variant of what about the power? So you just bring in the relevant equation. And the same thing for thermistor, instead of LDR, they can ask you about thermistor. And the trigger for thermistor would be, of course, temperature. So this is one concept that has appeared consistently in every single paper, not year, every single session, every single paper in the most recent exam sessions. This is diffraction grating. And every time you come across the diffraction grating, you just recall the relevant equation. Like I said, Unit 2 is heavily dependent on equations. So the equation is d sine theta equals n lambda. Okay, and d might have to be found out separately, and d is equal to 1 by lines per millimeter. But when you place the value of d over here, make sure this is in meter, because wavelength has to be in meter, and n is the order of maximum. Okay, for example, if this is the first order of maximum, the value of n is 1. But if this is the second order of maximum, this would be 2. And sine theta, theta is this, everybody. Okay, the angle that these two lines subtend. And this is also a likely topic that might appear in your exam, that is Huygens construction. So you see the three phenomena, right, that can be explained using Huygens construction: refraction, reflection, as well as reflection. In any situation, you just recall what Huygens construction is. Every point on a wavefront can be thought of as source of secondary circular wavelets, and these waves superpose. Okay, and the definition is of course given in the definition sheet, and detailed description is given in the fact sheet. And there are other years that this has appeared in. So be very wary of this concept. So when it comes to polarization, there can be some conceptual questions. For example, what is the difference between plain polarized and unpolarized light? How can you check if the light source is polarized or unpolarized? And how can you see objects underneath the surface of water? Which is basically another way of saying how can you reduce the glare from water surfaces? And not so common is this, but of course in the syllabus. How can you measure the angle of rotation of plane of polarization? So these were all conceptual questions, right? Very straightforward. By the way, there are no calculation questions with polarization. What they can also ask you is some contextual question. For example, you see, when I hold my sunglass, that's me, by the way. When I hold my sunglass like this, I can see through the glass and look at the screen, and I can see the screen. But the moment I rotate this 90-degree, the screen becomes invisible. That's because, one, my sunglass is polarized, and light from the computer screen is also polarized. So when the plane of polarization is parallel to the plane of oscillation, then and only then light is transmitted. But when it is perpendicular, as in this situation, light gets absorbed or filtered and no light is transmitted. Okay, so it's been years, several years, that there has not been a question about interference. Okay, so what's going on here is wave comes out from here, diffracts from these two openings, and undergoes superposition. And at this point, the two waves from these two sources are in phase. So constructive superposition takes place, which gives you a maximum. And when you move, the phase difference changes, the path difference changes, right? And at one point, when the two waves are in antiphase, the waves superpose destructively, and what you end up with is a minima. So what I've done is I have um, drawn some waves, as in wave fronts, to this diagram. By the way, this is a Jan 23 question. And, oh, sorry, this is what's happening. This is how the whole thing progresses. Okay, so I want you all to go through this concept very carefully, because it's been years that they have not asked a question regarding this. And when it comes to superposition, what they have been asking so far continuously is the standing wave questions. And by the way, what I wanted to show you was from these two slates, this is how the waves come out of the slates, diffract and superpose. And there can be some path difference calculations. Okay, so let me show you just one. Let's say they can ask you at this point P, and similarly at this point Y, what will be the path difference or phase difference? Okay, so always remember, for questions like this, path difference is the difference in path lengths. Okay, so this length is, let's say, S1P, this length is S2P. These are the two path lengths, and when you subtract these two, what you end up with is the path difference. But wait, this will not tell you whether the waves construct if the waves superpose constructively or destructively. If the path difference is a whole number of wavelengths, then constructive superposition, then it's a maximum. And if the path difference is an odd number of half wavelengths, then destructive superposition, and this point would be a minimum. Same thing goes over here. Okay, you find out the path lengths and subtract them to get the path difference, and then you check and you compare if the path difference is if it's a odd number of wavelengths, odd number of half wavelengths, or if it's a whole number of wavelengths, as in if it's n lambda or n plus half lambda. This is way more common, standing waves. So you need to have a very clear idea about standing waves in wind instruments as well as in string instruments, or in closed-ended tubes in the more rudimentary sense, and in strings. Okay, so this here, this pattern shows that the string is oscillating at f naught, and at f naught, the length is equal to, look at this shape, this is lambda by 2. But for closed-ended tubes, sorry, if one end is open and one end is closed, for these, always remember, at the open end, there is an antinode, and at the closed end, there is a node over here. And if you look at this shape, here, the length is equal to not lambda by 2, this is lambda by 4. Okay. And again, when it comes to questions like this equation is also very common. V equals to root over T by mu. T is the tension, mu is the mass per unit length. This equation only applies to standing waves in strings. Okay, always remember that every time you come across the term mass per unit length, there is only one equation that is related to, that is V equals root over T by mu. And V is not the speed of the standing wave. V is actually the speed of the progressive waves that reflect and superpose and then form the standing wave. Okay, so there are progressive waves being traveling here, right? And these progressive waves superpose to form the standing wave. And this V is the speed of the progressive wave. One thing I forgot to mention in this concept was, why are we using two different slits? Why not, let's say, two different sources like this, right? So it can produce waves like this and they can superpose, right? So this is also a very common question. We don't use this because this in this situation, the waves would not be coherent. This is a very important concept and definitely covered in the definition sheet. What do you mean by coherent? Okay, so for the refraction part, this part is really important. Sometimes this has become a recent trend of sorts, right? Deduce whether the ray will be totally internally reflected at this boundary. So what you do is you measure this angle. Let's say this is I, okay? And you actually find out what this I is. This whole thing is 90, and 90 minus 45 is actually 45, of course. So angle of incidence is 45. What you need to check is if this light will be totally internally reflected. So the idea is, for total internal reflection, angle of incidence must be greater than critical angle. Right? Angle of incidence must be greater than critical angle. And what is critical angle? Critical angle is that value of the angle of incidence for which angle of refraction is 90 degree. Okay, so you need to check what is my critical angle here. So the equation you recall is n1 sine theta 1 equals n2 sine theta 2. Let's say n1 is the refractive index of glass. So in the more dense medium, as in the higher refractive index medium, so this is sine c equals n2 is in air, which has a refractive index of 1 times, if it is actually critical angle, always remember critical angle is that value of angle of incidence for which the angle of refraction is 90. So this is sine 90. So you find out what is the value of C. Of course, the value of N will be given to you. So you find out C and then you compare the value of C with 45. If 45 is greater than C, then it will undergo total internal reflection. And if 45 is less than this C, it will not undergo total internal reflection. Okay, now comes the moment of truth, the last topic, nature of light. What I see a lot of times is students mixing up these two concepts in nature of light. One is photoelectric effect, which is like very in a detailed format, detailed way discussed in the full syllabus revision video. Please go to that. The link will be in the description. So for this question, the equation you recall is energy of the photon, energy of the photon equals to phi plus kinetic energy. So what happens is a photon comes in, interacts with an electron, gives enough energy to the electron absorbs the energy and gets dislodged, right? So after giving the metal the work function, the remaining energy is transferred to the kinetic energy of the electron, okay? And a question can ask you, how does this photoelectric effect show that light behaves as particle but not wave? Okay, so this could be a common question, and this could be a common theoretical question. And when it comes to calculation questions, this is the one. This is the equation that you use. And for concepts like this is the experimental setup. You might be wondering, why do you need this experimental setup? Because for this kinetic energy, right? We know the equation for kinetic energy, half mv squared. The V of the electron cannot be directly measured, right? It has to be found out experimentally like this. What happens is you keep on increasing the reverse PD, okay? And at one point, even the fastest moving electron is stopped. How is it stopped? Because of work done by the electric field. So the fastest moving electron has some kinetic energy, and this kinetic energy is equal to the work done, right? And there was a question in the most recent paper where you had to use this concept. And this work done is not your mechanical work done, as in force into displacement. This work done is actually this work done is electrical work done, and the equation for electrical work done is QV, and this is that V. And the V for which kinetic energy or the ammeter reading becomes zero, as in the fastest moving electron is stopped, is called the stopping PD. Remember this. And this QVS is equal to my kinetic energy. Then you have energy level transitions. And guys, this is where most students mix up these two concepts, because even here, an electron comes and the photon absorbs the energy, photon energy, and rises, right? So students mix this up, I feel, because here also photon is being absorbed by the electron, and in the photoelectric effect over here also the photon is being absorbed by the electron. But you have to understand the two locations. This is on a metal surface, and this is happening inside an atom, okay? And for this energy level transition concepts, always remember energy of the photon is always equal to the difference in energy levels, always, okay? And all calculations involving energy level transitions are based on this. And using energy level transitions, there could be some applications. For example, you have a continuous spectrum, but if photons are being emitted, right, for whatever reason, you end up with emission spectrum. And if photons are being absorbed, you end up with absorption spectrum. Okay, emission spectrum could be for discharge tubes, and absorption spectrum, the situation would be when you study light from stars, right? You'll see that it is not a continuous spectrum. There are some missing lines because photons are being absorbed. Then you have electron diffraction, right? So when you pass a beam of electrons through a diffraction grating or diffraction tube, sorry, not diffraction grating, uh, this is called a diffraction tube. And when you pass a beam of electrons through a graphite sheet, to your surprise, you see a diffraction pattern like this. You might be wondering, wait a second, are we dealing with electrons? Yes. And are we seeing a diffraction pattern? Yes. So diffraction is a wave phenomenon, right? So the fact that electrons can exhibit wave phenomenon tells us, or told us for the first time, that electrons can behave like waves. And if they behave like waves, they must also have a wavelength. And that's what you call the de Broglie wavelength. The equation is lambda equals h by mv or h by p. Now I have some final suggestions for all of you. Always start with section B. Mark numerical values in the question before starting the answer. Be very wary of the significant figures in the calculations. Do not forget to give units in your answers. A lot of times students miss out on their desired grades because they just forget to give the units. Memorize the definition sheet and the fact sheet inside out. In 3 marks or above mark questions, always apply the modular approach. Just get started with whatever information you have available, and this will guide you towards your final answer. And in any question, try to recall and relate the relevant equation. Good luck. And do let me know in the comment section where you are watching my video from. And best of luck one more time for your exam tomorrow. Take care and don't forget to subscribe.